Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at how tightly ligands can bind to a metal complex using a specialized equilibrium constant, namely the formation constant. So whenever we're generating one of our complex ions or coordination compounds, we need to have a specific reaction to figure out how these complexes form. So we call these reactions formation reactions. And more or less what they include is the coordination of the metal to any of the free ligands to generate the whole complex ion group. And if we want to try and figure out, well, how favorable is it to form one of these complex ions, we go ahead and use the corresponding equilibrium constant, also known as the formation constant, which will always be products, which is generally the complex ion being formed, over reactants, which should be all of the metal and all of the ligands involved. However, make sure that you keep an eye out for any stoichiometry involved with the number of ligands being coordinated. And it is worth noting, a lot of these equilibrium constants are going to be fairly large. This aluminum oxalate complex, for example, has a equilibrium constant on the order of 10 to the 16th. That is a huge number. And compared to a lot of formation constants, this may even be considered on the smaller range. These tend to be fairly stable compounds. And as a result, if I'm going to go ahead and try and figure out how likely this complex is to form by, say, mixing together some concentration of aluminum and oxalate, well, I'm going to essentially treat this as a completion reaction. As any of the oxalate will essentially scavenge all of the free aluminum until there's none left, guaranteing that we're almost entirely going to be products, or again, our complex with very free oxalate, very free aluminum and some oxalate present. So let's go ahead and work this as an example. So if I've got a starting concentration of 0.01 molar aluminum and 0.1 molar oxalate, well, first thing we can do is note that the volume of the solution isn't changing. So this isn't a titration reaction. And as a result, I can go ahead and model this using an ice table where I'm going to use molarity instead of moles because I don't have to worry about any potential dilution. Everybody has the same volume, so it'll be just easy. So then what we can go ahead and do is look at the reaction of the aluminum plus the oxalate goes to the aluminum oxalate. Then bring in the stoichiometry. For every one aluminum we consume, we'll consume 3 of our oxalate molecules and produce one of the coordination complex. So then we go ahead and have to figure out who's limiting. So this can be a matter of seeing who goes to 0 first. In this case, aluminum will go to 0 first with an X of 0.01 molar. And this gives us an oxalate concentration of 0.07 molar. And using these values, what we can do is, now that we've assumed the reaction mostly goes to completion, we can look at that back reaction to see how much aluminum will actually be generated once the system reaches a full equilibrium. And so in order to do this, we'll go ahead and construct our new ice table, where this time we're going to be starting with our aluminum oxalate compound and producing some free aluminum. And at equilibrium, we're going to be assuming that X value is super small. So my equilibrium aluminum oxide concentration should be about 0.01 molar, and the oxalate concentration should be about 0.07 molar. However, the aluminum will actually just have a value of X because it's not a plus or minus anything. There is no number to correct. So we can then take these values and plug them into our formation constant. Again, with a value of 0.01 molar for our complex and 0.07 molar for the oxalate, remembering to raise it to the 3rd power. And then our value for X goes into the aluminum concentration. And since we know what the formation constant is for the generation of this complex, we go ahead and rearrange this equation to solve for X, where X should give me the concentration of free aluminum in solution. And when we do this, well, we get something kind of fun, because the free aluminum concentration turns out to be about 1.5 times 10 to the negative 15th molar. This is also known as 1.4 femtomolar. If you're not familiar with femto as a prefix, that's fair because it's really small. We don't encounter it very often. Really illustrating, though, just how good so many of these chelating ligands and even general ligands are at binding up free metal. So in general, one of the reasons why we use a lot of chelating agents in chemistry and even in biology is they are an incredibly effective way at binding up free metal ions from solution, as long as you have a little bit of excess of your chelating ligand. And we can go ahead and see if we look at any number of these formation reactions. Most of these formation constants tend to be very large. So for example, if I'm trying to bind up cobalt with amine, we have a reaction on the order of 10 to the 33rd. Even on the smaller side, we're seeing 10 to the 7th and 10 to the 8th, which we would, in normal circumstances, still consider to be quite large equilibrium constants. So if you see these very large equilibrium constants like 10 to the 42, those are not a mistake. These ligands tend to be just that good at binding up free metal. So next time, we're going to go ahead and try to apply some of the tricks that we have from these coordination reactions to see how we can scavenge up those metals from solution to make a ionic solid a little bit more soluble. Until then, take care.